Hi everyone. So this is just a video to explain what to do with this worksheet which says two slit interference patterns. So you will find that as one of the attachments that I sent you for waves. Now what I have done is these are two slits, 1 and 2, and there are circular wavefronts coming out. So I've actually color coded them on paper, and so that makes it a bit easier. So I'll just show you what I've done. Okay, so these are parallel wavefronts approaching two slits, and the slits are about the same size as the wavelength of the waves, so they end up with two sets of circular wavefronts. So the first thing you would like to do is color all the waves, circular waves coming out from S1 one color, so I've done that as red, and all the waves, the circular wavefronts coming out from S2 another color, I've got that blue. Now, if you look closely at this, there are bold lines and there are dotted lines. So the bold lines stand for crests of the wave, and in between the bold lines, the dotted line stands for trough, and that's given over here. Okay. Now, what you get is what's called an interference pattern. And so if you look at all the regions where the crest intersects with a crest, or a trough meets a trough, you end up with a line of those, okay, like I showed in an earlier video. So these lines are called antinodal lines, the bold lines. Okay, so the bold lines are antinodal lines. It's the first thing you've got to do. And then you've got where a crest meets with a trough, and those are the areas where it cancels each other. Those are called the nodal lines. Now, both the nodal lines as well as the antinodal lines are numbered, and they're numbered from the center outwards, and this is called an order number. So the central antinodal line, n equals 0. Okay, and I've color coded those as well. So I've done pink for antinodal and green for nodal, and then so that's your central antinodal line. The next bold line is this one, that's n1, and the one beyond that is n2. Similarly, on the other side of n0, you've got your n1 and you have your n2. So those are your order numbers for antinodal lines. Now, in between the antinodal lines, you've got your nodal lines, and those are also go 1 and 2 on the side, 1 and 2 on the other side. So that's how we've answered questions 1 and 2. Now, the next thing we have to do is figure out what is path difference. So the question reads, state the path length in numbers of wavelengths for each wave at positions A, B, and C, and hence find the path difference. Note the relationship between path difference and the order number of the antinodal line. So the path difference is the difference in distance traveled by the waves to reach a point. So this is point A. Okay, so to figure out how many waves from S1 reach A, how many waves you got to count. So from there to there is 1 wavelength, 2, 3, 4.5. So that's I got 4.5 here. And then from A to S2, now those are the blue waves. Okay, so there's the blue ones. So 1, 2, 3, 4, 5, 6.5. That's I got 6.5. And 6.5 minus 4.5 is your path difference. So the path difference is 2 wavelengths. Okay, similarly for B, so here is B, again where 2 crests meet. So let's count how many red waves there are. So there's 1, 2, 3.5. So I got the 3.5 from S1, and the blue you get 1, 2, 3, 4.5. So 4.5 from the other slit, and so the path difference is 1. Similarly for C, C is over here in the center. So these are where 2 troughs are meeting. That's also an antinodal point. It could be 2 crests or 2 troughs. So looking at the blue, you got 1 and 2 wavelengths from S2. And then looking at the red, 1, 2 wavelengths from S1. So you got 2 wavelengths minus 2, you get 0 wavelengths. So the path difference in terms of the order number and wavelengths is n lambda for an antinodal line, where n can stand for 0, 1, 2, 3. So just look at this. So for A, which is on line number 2, n equals 2. Path difference is 2 lambda. B is along n equals 1. See the B there? Okay, so the path difference will be just 1 lambda. And C is along the central antinodal line where n is 0, so the path difference is 0 wavelengths. All right, so that makes sense. Now just look at for antinode points along the antinodal line. So there's D, E, and F. So here is D. So I'll just show you for 1 and then we take it on from there. So from S1 for D is where a bold line and a dotted line are meeting. So the red ones is 1, 2, 3.5. So that's how I got 3.5. And then the blue ones are 1, 1.5. 1.5 wavelengths. So sorry, the red ones are 3 and the blue ones are 1.5. So that's how you get 3 minus 1.5, you get 1.5 wavelengths. Similarly, for E, you have half a wavelength, and for F, you get 1.5 wavelengths. So your D is along antinodal line 2, and the path difference is 2 minus half is 1.5 wavelengths. And your E is along, your nodal line n equals 1, and so your path difference is 1 minus half wavelength. So that is how you get that. So if something, so for antinodal lines, it's that n minus half. Okay, so that's how you get that. And the answers are here at the bottom. I hope that made sense.